Continuing our investigation of dimensions of vector spaces, we're going to look at what we can say about the dimension of a subspace of a vector space. And that is summed up in this proposition here. It says if you have a subspace U of a vector space V, then first of all, the dimension of U is less than or equal to the dimension of V. And secondly, if their dimensions are equal, then actually U is equal to V. Let's look at how to prove these using the results we've just seen about bases. So firstly, let's notice what we can say for number one. Let's think about what we can say about a basis of U. So a basis of this subspace U, well, thought of as elements of V. They may not be a basis of V, but they're certainly still linearly independent. The reason they're not a basis necessarily is they might not span all of V, but certainly they are still linearly independent. So this is a linearly independent sequence of elements of V. So we can extend it to a basis of V. So what could we say about the size of this basis? Well, one thing we could say is the size of a basis of V is the dimension of V. But another thing we could say is that we got this basis by extending the basis for U, so it's at least as big as the basis for U was. So in conclusion, the dimension of V is at least the dimension of U. Moving on to the second part, we've got to show that if we've got a subspace U of V which has the same dimension as V, then actually it is equal to V. So what we'll do is we'll suppose for a contradiction that that's not the case. So we're supposing that the dimension of U is equal to the dimension of V, but actually U is a proper subset of V. So U is contained in, but not equal to V. So that means there exists an element of the vector space V which is not in U. So there exists V, an element of V which is not in U. So let's take a basis of U. So U1 up to UN, let's say, be a basis of U. So, in particular, the span of U1 up to UN is U. A basis has to be a spanning sequence. So this vector V is not in U, which is the span of U1 up to UN. Now, this is the right situation for us to use the extension lemma from 2 videos ago, maybe 1 video ago, I can't quite remember. But the extension lemma would then tell us that the sequence obtained by adding V on the end of U1 up to UN is still linearly independent. So U1 up to UN and then V is linearly independent. But now, what have we got? We've got n plus 1 linearly independent vectors in a vector space of dimension n. This is our contradiction because we know that any dim v plus 1 vectors must be linearly dependent. We proved this in the last video. So by contradiction, U must actually be equal to V. So that's what we can say about the dimension of a subspace. And let's see why this is, one reason that this is useful to us. One reason is that it means, or enables us to prove that if you've got a vector space V whose dimension is n, then any n linearly independent elements of V must form a basis of V. And the proof is now really easy, because if you've got those n linearly independent elements, so let's say L1 up to Ln be linearly independent elements, then what you could say about this is that if we give a name to their span, so let's call it U, we have that the dimension of U is equal to n, because L1 up to Ln is a basis for U. It is certainly linearly independent, and by definition its span is equal to U. So by the previous result, U is all of V. Okay, so what do we now know? We know that L1 up to Ln is linearly independent. We know that the span of L1 up to Ln, which we called U, is actually equal to V, and therefore L1 up to Ln is a linearly independent spanning set for V. That is, it's a basis for V. Okay, so if you happen to find n linearly independent elements in a vector space of dimension n, then you know immediately that it must be a basis. You don't have to check that it is a spanning sequence. It has to be a spanning sequence. So you can, using this method, if you know the dimension of a vector space, it enables you to skip checking part of the definition of a basis, because as soon as you've found n linearly independent elements, they must span. Okay, finally, let's look at our last result on dimensions of subspaces. And just before we read any of this stuff, let's think about a bit of motivation for this, which is vector spaces and dimension is a bit like finite sets and size. So when we thought about the sizes of finite sets, we did this thing which was a special case of what's called the inclusion-exclusion formula. So that was, let's say you've got two sets, A and B, so two finite sets, A and B. So the size of A union B, well, it's not just the size of A plus the size of B, because if you have this if you add the size of A to the size of B, you're double counting. You're counting everything which belongs to A and B twice on the right-hand side. So you remember that you have to subtract off the size of the intersection of A and B to make that formula correct. So if finite sets and size is like vector spaces and dimension, then there should be a similar formula for subspaces of vector spaces. So if we replace the union with the sum of subspaces and we keep intersection as intersection, there ought to be a similar result to this. And that similar result is that if you have a vector space V and you have two subspaces x and y, then the dimension of x plus y, which is like the size of A union B, is the dimension of x plus the dimension of y minus the dimension of their intersection, which is like size of A plus size of B minus size of A intersect B. So we ought to be able to prove this, and we are now happily in a position to be able to do that. So I've written up the way the proof works. What we do is we begin by starting off with a basis of x intersect y. So let's say our basis is z1 up to zk, so that the dimension of z1 of x intersect y is k. So let's write this down. So dim of x meet y is k. Now this is a linearly independent subset inside x, so we can extend it to a basis of x. So we'll have some notation for what happens when we do this. We end up by taking a basis of x intersect y and putting in some more vectors. So we'll end up with z1 up to zk followed by some more vectors x1 up to xl. So in this case, dim x would be equal to k plus L. And similarly, z1 up to zk is a linearly independent sequence inside y, so we can extend it to a basis of y. And if we introduce this notation for that basis, so the z's followed by some other things which belong to y, we say we added m new things, then the dimension of y would be k plus m. Now, I claim that it's enough to prove that the z's and the x's and the y's together are a basis of x plus y. And the reason that's true is that if we proved this, then the left-hand side of our equation would be k plus L plus m, because there will be a basis consisting of the k z's and the l x's and the m y's. And then on the right, you would have the dimension of x, which is k plus L, the dimension of y, which is k plus m. And when you add them together, well, you're too large by k, but that's exactly what you'd be subtracting off. So if we prove that that thing is a basis of x plus y, then we've proved the dimension equality that we wanted. So let's just try and do that. So first of all, spanning. We have to prove that that sequence is a spanning sequence for x plus y. And this is reasonably easy because elements of x plus y look like an element of x plus an element of y. So we'll let x plus y be an element of the vector space capital X plus capital Y. Now, since, of course, I'm assuming here little x is an element of big X and little y is an element of big Y. So x is going to be equal to, well, it can be written as a linear combination of our basis for x. So it's going to be, let's say, a sum of ai zi plus a sum of bi xi. Those things were vectors. So for some scalars, let's just tidy that up. ai and bi. And similarly, y being an element of capital Y, it can be written as a linear combination of the elements of our basis for y, so it should be some linear combination of the z's and of the y's. Okay, now if we look at x plus y, that is equal to, well, I can gather together the z's, so I'll get the sum of ai plus ci times the z's plus the sum of the bi xi's plus the sum of the di yi's. Okay, so we've shown that any element of capital X plus capital Y is a linear combination of z's and x's and y's. In other words, that the z's and the x's and the y's are a spanning sequence for x plus y. So the thing we have to do next is linear independence. So let's suppose that we have a linear combination of those things which is equal to the zero vector. So we'll suppose that a sum of, let's say, ai zi, so this sum should go from 1 to k, plus the sum of bi xi, this sum goes from 1 to l, plus the sum of the ci yi's, is equal to the zero vector in our vector space V. So here ai and the bi and the ci are some scalars, and we have to prove that the a's and the b's and the c's are all zero. So how can I do this? Well, one thing that I'm going to do is I'm going to rearrange this a little bit. So we're going to rearrange this equation by moving the y's onto the other side. So if I move the y's to the right, I'll get that the sum of the ai zi's plus the sum of the bi xi's is equal to minus the sum of the ci yi's. Okay. So what can we say about the left-hand side and the right-hand side of this equality here? So on the left, you've got an element of x, because the z's all belong to x intersect y, so in particular they're in x, and the x's all belong to x. So the left-hand side is in x. So LHS is short for left-hand side, that's in x. And the right-hand side, so RHS is short for the right-hand side, that's minus the sum of the CI times YI's. Well, the y's all belong to our subspace capital Y, so this is a linear combination of things in that subspace. So the right-hand side is in Y. Okay, but the left-hand side is equal to the right-hand side. So both sides belong to X and they belong to Y. Okay, so let's move on to the next slide and see what we can say. So since the right-hand side, which was minus the sum of the CI/YI's, is in X and in Y, so it's in the intersection, we can write it as a linear combination of our basis for X intersect Y. So it's equal to some linear combination, let's say DIZI. Okay, what have I got then? I've got minus the sum of the CI/YI's is equal to the sum of the DIZI's. Okay. So just kicking the y's back onto the right-hand side of this equation and then flipping it over, I'll get the sum of the DIZI's plus the sum of the CI/YI's is equal to the 0 vector in V. Okay, but now you can see we have something interesting, because the z's and the y's together were a basis of y. Let's just write that down properly. So z1 up to zk, and then y1 up to yl were a basis of y. So they're linearly independent. And if they're linearly independent, and we've got this linear combination of them being the 0 vector, all of our scalars in that linear combination must be 0. Okay, in particular, all the c's are 0. Right, but we could make exactly the same argument, only instead of moving the y's onto the right-hand side, we'd move the x's onto the right-hand side, and that would tell us that all the coefficients of the x's are 0. So I will use my favorite word. Similarly, all the bi's in my linear combination must be 0. So if I know the c's and the b's are 0, our linear combination is now, well, I can forget about all the b's and the c's. They were all 0, so they don't give me anything. So all I've got is the sum of ai zi is equal to 0, the 0 vector. All right, but the z's were a basis again. So z1 up to zk was again a basis, so in particular it's linearly independent. So all the a's are 0. Okay, we started with the linear combination, which was the sum of ai times zi plus the sum of bi times xi plus the sum of ci times yi equal to the 0 vector, and we've now shown that all of the a's, all of the b's, all of the c's are 0. It follows that the z's followed by the x's followed by the y's, let's get these indices right, is linearly independent. We've shown that it's linearly independent. We've shown that it spans x plus y. So it's a basis for x plus y, and we're done.